Hello, everyone, and welcome to this last lecture of Hacking in C. We will be wrapping up today with all of the lectures in the course. Today we'll be talking about slides, not my presentation software. Today we will be talking about many things. But mainly we'll be focusing on defeating the types of protections that so far we've been turned off. This is not anything that you'll need to complete the assignments at the end, but it is good to know that the protections that we talked about already last week are not the be-all, end-all of protections, and that you still need to make sure that you avoid the types of problems that we've been exploiting during this course. At the end, I have a little bit on where I compare C to Rust, a much more modern programming language, and there I will explain that it is not necessary to have all of the problems that C has, it is not that you need to have those problems that C has in order to get the types of performance that you get and the type of control that you get when you program C. You can also get all of that in safer languages just by strengthening the language in certain ways, but that's at the end. First, we'll start a bit with a recap of last week. So we talked about overwriting buffers to take over the control flow of a program. We overrode local variables, the return address, and we used shellcode. And we talked about constructing shellcode, which was bytecode to spawn a shell. And you used all that to complete this hacking assignment. Last week, I guess not, but the week before, because last week was Pentecost, of course. When we constructed the shellcode, we used these tricks to stay clear of null bytes, and we talked a little bit about mitigations. Having less code, so there's less to exploit, using safer languages, or relying on tools such as dynamic analysis and static analysis that can help you find problems in your source code. We also talked about protections like stack canaries and write XOR execute. Something that I want to come back to is the general plan of attack in these things, where this is sort of the general structure that you need to do. If you follow this systematically, you can get quite far also in the exercises that we'll present tomorrow. So you first need to start with looking what is there, what is vulnerable, what happens in unexpected ways when I, for example, give 100 A's or 200 A's or 4,000 A's. Does the program crash, or does it just treat that normally? Do I see some garbage being produced? Do %p format strings lead to something else being printed than a %p? Then you know that there's a vulnerable printf. If you get a segmentation fault when you give in too much info, then there's probably a buffer overflow. And you need to try to figure out how you can see what's going on that other side. So if you're local, you can use a debugger, because that debugger opens up the black box that is a program and lets you look inside, but that of course doesn't work if you're doing it remotely. So there you will need to use format string attacks typically to do something. If you have a buffer overflow, try to figure out when it crashes. So when it crashes usually means that there is something that you're overwriting that was critical to the program continuing in a normal way, right? So is there a return address there, or is there a frame pointer maybe there? Because if those get corrupted, then the program will start to behave in a way that usually leads to a crash. And if you found all of those things, you need to think about, okay, I know now know this, I now know this, I know what the stack looks like, more or less. Then you need to figure out how you're gonna go about reaching your goals. So you can take over the return address to execute other functions, find those functions' addresses, and then you could overwrite the return address with that address. That's what you saw in assignment 4, where you had to use the launch shell function. You were given that address and you needed to overwrite the return address to run that program. Or if the code is not present in the program, you'll need to inject your own. And that was the shell code that we talked about. If you want to use shellcode, though, then you need to put it somewhere. Well, usually there's some buffer where you can put it in. And then you need to figure out what is that buffer's address, and then take that address and put it in the correct place. And then if you had some trouble figuring out that address, for example, because it was incorrect, at the end of the last lecture, inaccurate, for example, you only have a frame pointer and you figure, okay, well, it's the frame pointer minus some amount of bytes. Then you could use knobs to overcome such imprecise ideas of what the return address should be. The exam assignments, you will have the entire time to do it, and you don't need to do those in one go. I will go into the exam in much more detail tomorrow. So first, something that was very fun that I saw this week. There is this game called TicTacToe. You might be familiar with it. And let me switch over to a terminal. So someone made a very nice implementation of TicTacToe. Oh, I don't want to compile it to there. You can see I can compile this program with all of the warnings turned on. Everything is super great. And then I can play the game of TicTacToe. That was a bit of a dumb move. 6, 9, and now X, of course, has lost 4 and 8. Okay, now whatever. Player 1 wins. Great. Super simple game. Very fun. I will now show you the source code for this program. Move something out of the way. This entire program is a printf statement. While printf. And this is the format string that is being used. And I hope everyone will appreciate the ASCII art here. And of course, your question should now be, why? Oh. Well, this was a submission to the International Obfuscated C contest, where people write the most convoluted source code possible. But not only was it a nice submission to this contest, the authors proved that printf not just is the one true debugger, but also a Turing-complete piece of code, which means that you can implement any program in printf, just in printf. Yeah, that is kind of amazing. There's a link in the slides. But I thought this was very fun and relevant to what we've been doing to show you this piece of code. It shows you again that printf is completely horrid and broken, and you should be very careful. Yeah, the authors introduce printf-oriented programming, which is a nice pun on what we're going to talk about next. That is defeating write XOR execute. That was this idea that you have these data pages that are either writable or executable, and then you could mark the data, so where you put your variables for programs in as a writable segment, so also both are readable, of course. There you can modify things, increment an integer, those kinds of things. And then there's the code segment where you put the bytecode of an executable, the source code that's being loaded, and then step-by-step run. And then if it's marked as executable, the CPU and the operating system together make sure that any writes to that segment get eliminated. And similarly, that every time the CPU tries to load code from a piece of the memory that's marked as writable and not as executable, it will also say this is not something that I'm gonna allow, segmentation fault. This was the kind of protection that we had to turn off when we were doing all of these shellcode-based attacks, because precisely that kind of attack is what W XOR X is supposed to prevent. Injecting code into the binary, into this data segment, and then running that was exactly what the shellcode, of course, did. So we had to turn those protections off. Having this protection turned on means that we can only jump to the code that's already present in the program. We cannot add to it, because when we add something into the memory, we are writing it, and unless that page gets later swapped into executable, we can only jump to code that was already there and not add our own. So does this protection mean that it is the end of attacks on programs that do not contain a function that's called please give me a shell? Sort of. It turns out that there's a lot more code present in your program than just what is available in your program.c. Usually, most programs load at least the whole entirety of libc, because that is the library that contains all of the functionality, like printf, gets as format, all sorts of math functions, read line, get string, all sorts of usually functions that you use without thinking about them much. Malloc is in libc, and that is loaded into the memory of most programs. They also often load other libraries, additional maths libraries, something to draw a GUI or stuff like that. And then the question is, does libc maybe contain this function that's called give me a shell, please? Kinda. There's this function called system, and what system does is that it uses the fork function to create a child process, and in that child it will execute a shell command given by this character pointer. Well, that's of course going to be a string. So if you would call system and then bin as h, it should give us a shell. So if we can somehow prepare this argument for system, and that can be in the data segment because that's just data, we can overwrite the return address with the address of system, and then system will read the argument that we prepared, and then it should start the shell for us. And this is called returning to libc, because we are using the return address of something in libc to do our dirty work for us. But that means that we need to get this argument in place, which is tricky. In the days of yore, when we had 32-bit processors in most computers, there used to be the thing that arguments were passed via the stack. And putting stuff on the stack is easy. You just do buffer overflow, right? So we could get this address and this of libc and the offset where system was at to compute the correct address we need to overwrite. You can use some nice magic for that. And without any protections, all of these numbers are usually at the same place on the same computer. So this was just something that you could do. Then you would write the address where you put bin sh to the stack in place of the argument. And then after that, on the before that on the stack, you would overwrite. No, I'm saying that wrong. You would put that address on the stack because the arguments were pushed on the stack, and then the program that would be called would just pop them off. So you could put the return address on the stack frame, and then you would overwrite the return address with the address of system. And then you could even set it up very nicely if you wanted it to return. You could, for example, also push another return address to make it call exit to normally terminate the program. This you could do, for example, to prevent your attack from being detected by some program that monitored if the program crashes, for example. Nowadays, though, using 64-bit processors, we have much more registers than we used to have. We have 16 instead of 8, which means that it was deemed nicer to start passing arguments through these registers. The first 6 arguments, remember, are passed through registers. So how do we load this address of bin sh into the correct register, RDI in this particular case? Well, we're looking for a piece of code that does exactly this. If we have this, then we can get bin pop RDI and then return. And then what this will do is that it allows us to jump to somewhere, which will do our dirty work, and then it will jump back. And then if we can get it to jump again, then this is a sort of the thing that we're going to try to do. The thing is that there probably isn't just any function that does precisely that. But we don't have to jump to the start, to exactly the start of any function. It's pretty likely that this piece of code is somewhere, but then if we know that we can find it anywhere, then we can just jump exactly to this line of code and then execute it. So we can probably find it somewhere. And such a snippet we will call a gadget from now on. So having found this gadget, we can attack something, and we can do that in the following way. We overwrite the return address with the address of the gadget. So that means that we can, when the function we're in will return, it will go to the gadget. And remember, then the stack has already popped off the current stack frame. It's popped off the return address. So we need to put behind the address of the gadget the address of bin sh. Then behind that, we need to put the address of system. Because what will then happen is that the function will return, so it pops the return address from the stack. Then it goes to execute the gadget, and the gadget will pop the address of bin sh into the register and remove it again from the stack. And then it will pop the return address again, which is now the address of system, and then it will jump to it. And you might have noticed that this means that we need to write multiple addresses, which is super annoying because we'll need to write null bytes on AMD64. Because remember, an address is 8 bytes, but we only use 6 of them in user space. So there's always null bytes at the start of an address. we can make sure that there's a bunch of countermeasures to this kind of attacks, and one of those is that we can make sure that there's a null byte in the address of libc. That will stop functions from reading past it, and this is also, in fact, what makes this attack so hard to do on AMD64. But that only complicates string-based attacks. It could, for example, be that the vulnerability is in a file that's being read from the disk somehow, or being read from a database, and it's just a binary file. Or, for example, it's a JPEG processing library. Because in pictures, you'll find null bytes all over the place because it's a binary format. And if you then have a buffer overflow that will just copy things, this type of attack might still be possible. The other thing that you might think is a solution is remove functionality from libc. So, for example, take out system only includes the code for system in programs that actually use it, and then you might have code that is more secure because you cannot jump to the address of system anymore. But then you start getting into these problems of, what is necessary, what is not necessary. Will you run into all sorts of compatibility issues? And the problem is, what code exactly can cause problems? And I saw that there was a question about a pop RDI, that this pop removes something from the stack, so it loads something from the stack into RDI. So it will take something off the stack and put it into this register, which is exactly what we want to do. This type of attack is maybe a bit what's going on here. It is something that you might want to go through slowly, carefully tracing all of these steps, maybe on a piece of paper, but that's somewhat hard to do, unfortunately, in the current situation because I don't really have a blackboard. So let's return to there's another question. No, pushing and popping is something that is when we talk about the stack, because the stack is this pile and you can put things on top of the pile or take it off the pile. And usually when you say you push something, you do it from a register onto the stack. So that's when you say you push a register. When you pop into a register, you pop it off the stack and put it into the register. Note that when you push something from a register, it's not like that zeroes out the register. It will just keep the data that is there because you might want to push it again or use it again in some other computation, etc. So you shouldn't see it as pushing to RDI, but you do load into RDI. Returning to where we were in the slides, removing functionality from libc is tricky because it's very hard to see what code exactly can cause problems, and that is amplified by the fact that we are not just restricted to the functions that are there. So removing system doesn't really work because we can use any gadget at any arbitrary address, and we can chain many of such gadgets as long as every one of them ends in a return or a jump if you use slightly more advanced attacks. And you can use those gadgets to construct any code that you want. This is proven to be Turing complete, in fact, just like printf has been proven Turing complete very recently. Return-oriented programming is what it's called, and it enables malicious computation without malicious code. It was invented in 2007, and it won 10 years later a Test of Time award, which is this award at this conference that they give to research that 10 years ago was published and still has proven to be very relevant. And I think they rightfully probably won this award. I've not seen the competition. And the problem with this technique is that it's very powerful, because libc already contains enough gadgets to allow return-oriented programming to be Turing complete. You can construct a Turing machine from the gadgets that you can find in libc. There are tools that can even automate the search for these gadgets, and in some extent even the change. So you can tell some software, I want to do this, and then we'll try to figure out the right addresses that you can put in the right order to do arbitrary computation. And that again is computation without injecting new source code. You're not injecting new assembly code, you're just using what's already there and only writing these addresses onto the stack. So this is not something that write XOR execute can prevent. So we have an example here, and this is a example where we have a bunch of different gadgets. So we have a function that we're currently executing. Then we have OX feed phase, which does an XOR of RAX, excuse me, with itself. So what this gadget does is it zeroes out RAX. Then we have the Cafe Babe gadget, and that's the one we saw earlier, and that's the one that pops something off the stack and loads it into RDI. And then we have this dead beef gadget, which moves RAX into RDX and pops RSI. And in the execution of vonfunc, there was some corruption going on, and that allows us to push all of this onto the stack. And this is the top of the stack, so we're starting from the bottom here. And as we start to return, we will pop the address of Cafe Babe into as the return address. So it will return to Cafe Babe. You'll see that Cafe Babe, we can just happily jump into there. It's in the code segment, so we don't need to worry about write XOR execute, and it will just pop something off the stack again. And you'll see that we've set -h into RDI. And we return again, which means that we pop the feed phase address, and that thing executes the XOR, it zeroes out RAX, and then it returns again, which means we pop the return address. You might see the pattern here in return-oriented programming. That beef, again, does something to these registers. It also zeroes out RDX, and then we will return again. No, we will first pop again. So this pops RSI, and there it again sets it to -h. It might also have been suitable to find another mov instead of this pop. So you would mov this thing to this thing. Many ways to do this. We return again, and the return address that we're now on is the location of execLP, which is an type of function that you can use to start to execute another process. So we will now start -h using these arguments. This type of attack is quite powerful, and it is something that prompted the introduction of ASLR. That is a protection that's based on the fact that these attacks that we've used, both return-oriented programming and shellcode-based attacks, they both required us to know exactly where we needed to go. And especially for return-oriented programming, we needed to very exactly know where we needed to go. Because if you're 1 byte off, you will be in a different place, will be executing more code than you want, and then your stack will probably get messed up, and that's not what you want. Shellcode can usually work around some amount of randomness with a large knob set and some brute force. And we have been switching off address randomization throughout our exercises because it makes life hard, because otherwise we need to defeat randomization. And we have been doing that using this set arg command, and it should be quite familiar to you right now. But that brings us to ASLR. What exactly is the thing that we are turning off with this address randomization thing? It was invented by a bunch of anonymous people, actually. The PAX project, who the author of which is anonymous. And they published a bunch of patches for hardening Linux. I think they still do. In 2001, they proposed ASLR. They also wrote a white paper sort of explaining the idea, and then it was first enabled by default in OpenBSD in 2003. Linux followed a little bit later in 2005, that they merged it into mainline and turned it on by default. Windows, of course, has some compatibility issues, so while they gained support in 07 in Windows Vista, they only have it for enabled executables. And I think that's even still the case because they are just printer drivers that never get updated, and if you would start to randomize their addresses, they would simply not work anymore, they would crash. It seems, it was a bit hard to Google this, that Windows 10 randomizes more executables, but it's still not great. It seems namely that these addresses are only re-randomized every time you reboot, which means that if you can first read the addresses and then write the addresses a second time executing, you might still be in business. macOS has randomized system libraries since 07 in October, and all applications since 2011, and also even the kernel since 2012. Android requires all code to support ASLR fully enabled in Android 5. So this is something that has gotten a broad support in many executables and operating systems, and that is because it is such a powerful protection, especially against a ROP. There's a little bit of cost, but it's not too big, and yeah. But what is exactly what you're doing with ASLR? Address space layout randomization. You move around the locations of something. So the base address of an executable, libraries, and the stack and the heap. Moving around the stack and the heap are quite easy because you can just change the stack pointer and the heap allocator, both of whom are more or less managed by the operating system. Your program starts up and it just accepts some stack pointer coming from somewhere. So adding 100 bytes to it or removing 100 bytes to it is not relevant to how that program is going to continue to execute. Similarly, you just call malloc when you want something on the heap. The program will not expect anything structured from that pointer that's going to get. It's just getting a pointer. It's not allowed even to expect something predictable to happen there, except that it gets some amount of memory that is contiguous and it can do stuff with. So randomizing those is quite easy. And you see that that was the first level of protection that was implemented. The shared libraries are also loaded into your program at some address. And if you want to then randomize also the code within such a library, you need to compile it with ASLR support, because then they, whenever you have code that jumps somewhere, etc., it doesn't work anymore to say a jump to exactly line somewhere, because you will start to move it around. So you need to use relative instead of absolute addressing, and you'll see that if you enable the code with ASLR support, that it starts to generate all sorts of jump tables, etc. The technical term here is a position-independent code, but that's usually turned on by default by now. Compiling without FPAC can even be slightly hard if your system does not ship the correct position-dependent binaries. But then you can already randomize the libraries, and you can randomize the stack and the heap. Executables can also be enabled to be more randomized. That's -f position-independent executable pi. And then also it enables the operating system to move around the start of the executable in memory, and then you'll see also that local functions start to move around. Depending on your Linux distribution, all of this may be turned on by default. And that's more or less how it works. It moves around things by adding or removing some offset to where it's going to be in memory. So that brings us to defeating it. This offset is fixed at load time. So if you leak the offset, then you can use that to compute all the addresses using the offset, because you know, okay, it needs to be at least at that point, and then you can add the offset, and then you can compute all of these addresses. So how do you leak such a address, the offset? Well, if you have printf, then you get some pointer, and you know what you expect, and then the offset, and then simple maths, and then you can compute this address. Memory dumps are another good way to leak it, especially if it's not randomized every time you execute it again, but only at every reboot. If the program crashes, it might save a memory dump, and then you use this memory dump to figure out the offset, break it, many other ways. Another problem is if just one library is not randomized, you can still use return-oriented programming, because that library, by its own design, is expected to be in a fixed place, and we can use that fixed place to jump into it to do ROP. So you need to be very careful that all of the libraries are randomized, and it used to be for a long time that some libraries were not, and then you're still in heaps of trouble. Side channel attacks are also often used to leak the randomization. Most famous ones, Spectre and Meltdown. And another way to just defeat it is to guess. And guessing these things is something that brings us to the problems that we had with ASLR on 32-bit machines. There simply was not enough room for randomness, so we couldn't randomize the lower 12 bits because that needed to be fixed for technical reasons, and it would break page alignment. The upper 4 bits were necessary for large memory mappings, and then you remain already with only 16 bits of entropy, and I think there was even a bit more restriction on that. So that means that there's only 65,000 possibilities. Well, a birthday attack means that you can usually guess that in probably half that. And of course, if there's a system that's connected to the internet, you can probably guess a lot at the same time in parallel. You might be able to automate this. Attacks are often quick to execute, which means that this is not great. Fortunately, this is largely solved on 64-bit systems. I think the amount of bits that you have are at least around 2 to the 20, which is not cryptographically great, but it is still quite a large amount of room that things move around in. So it makes guessing a lot harder. And again, this is something that just makes attacks more expensive to do. Less reliable, more expensive, easier to detect, which is precisely the type of thing that keeps out many attackers, except the most motivated. So that was it for ASLR and for write XOR execute, the most popular and well-known protections that have been added to operating systems in the last decade or so. And these quite powerful protections really keep out a lot of the more trivial attacks. They just make them a lot harder. It might still be possible to execute something, to exploit something that's been protected with these measures, but it does make it quite a bit harder, especially when combined with stuff like stack canaries. Next up, we're going to talk about memory safety, but I think it's first time for a bit of a break. So I will see you again in 15 minutes, and then I will talk a bit about protecting yourself, or how you could design a compiler, a language to keep you from having these problems, or many of these problems at least, in the first place. And that will probably be not so long, and then we will be wrapping up with some announcements. Then we'll be finished nice on time, and then we can tomorrow talk about the exam, Q&A, the exercise that you did on hackme.rded.nl, and whatever comes up. So I will see you in 15 minutes at 16:30. Okay, we're going to continue now. So why do we have all of these problems? Why do we have the fact that we can overflow buffers, that we have use after free, that we can have all of these memory leaks? Well, in C and C++ and some other languages along the same lines, there is simply no information at runtime to check if we're within buffers. A buffer is defined as to just be a bit of memory. There's no size attached. That's not kept track of anywhere. So it's simply impossible to check if you're within a buffer. It's also not possible to reliably tell the size of a given buffer at runtime. So if you need to always pass along such a size or something, and that leads to unsafe designs. For example, memcopy, get as string copy. You have the memcopy, you need to be very careful about what size do you give it for what you want to copy. Get s simply reads whatever. String copy also does not care about the destination at all. It just cares about null bytes. And all of these things are examples of the unsafe design decisions that are a consequence of not being able to tell if you're within a buffer. And there's also no way to fix that, right? Because you don't have that information, or you could also not augment get as or string copy or memcopy to check if the buffer that you're copying to is large enough, because the function cannot tell. So that is tough. The compiler also allows definitions of variables without initializer. Pointers are completely managed by the programmer. The heap is a special kind of headache when you need to freeze something, etc. And many of these problems are also greatly amplified when references start to be shared between threads, because then you have all sorts of problems with locks, data races, where you have that threads start to update things in different orders, and then it's hard to remain consistent. If you pass something along to two threads, which one needs to free some heap variable at some point? This is all a bit tough. So there are a bunch of languages that try to solve this in many different ways, and one of those languages is Java that you might have seen. So all of the source code that you have is compiled to a special type of bytecode, and that bytecode that runs on a Java virtual machine. It's read there, and that virtual machine has some special features. It manages the heap, and it does something called reference counting, which means it keeps track of all of the references to pieces of memory, and it will automatically clean up anything that went out of scope. So when you call new, it will allocate something on the heap, and then the garbage collector and the in the JVM will every time once in a while it will see, okay, how many pieces of code still can access this bit memory, and if no one can access something anymore, then it simply will throw it away. It will check all of the memory accesses if they're within scope, because they all go through the JVM. And a downside of this garbage collection thing is that it will frequently suspend threads to do the cleanup, because it needs to pause everything generally, and then we'll need to go through all of the pieces of memory. Okay, does this have 0 remaining references? Can I then throw it away? That makes Java programs often to be experienced as if they would lock up often, for example, because then it was this JVM that started the garbage collector, froze everything, went through the memory to do cleanup, and then unfroze everything again. But that would lead to bad user experience, let's say. In Python, you have an interpreter. The source code is not compiled, but the interpreter runs it for you, and it does all sorts of checks. There's also no fixed size array type. All types will resize themselves whenever necessary. That even goes for integers. And Python is another example of a garbage collected language. Then there is Rust. And Rust tries to solve these problems in a slightly different way. They sort of start out from the observations that fixing bugs takes longer than spending more time on compiling things and checking things, because fixing a bug you might have experienced often will cost you hours. And it's also possible to generate code that has a lot of checks and a lot of balances, and then rely on a compiler, and they use LLVM as a compiler to just optimize everything that you can prove is unnecessary, to just take that out. And that means that you can start off with code that is in theory quite slow, but half the thing it's doing, the compiler can just figure out it's unnecessary and it will throw it out. And they also use the latest ideas in compiler design, etc., which makes the compiler a lot more complicated, but the code you get out of it a lot more reliable. So they do some smart things in the language. For example, they have fixed size arrays are typed with the size of the array. So this is an array. Let defines a new variable, and this array is a uint8, 8-bit unsigned integers, and there's 10 of them, and well, there's 10 of them. And the type really is, the size of this array is really part of the type. So that means that a 11 size array is a completely different object from a 10 size array. And what allows you this to do? Well, you can sort of generate functions for all of the array accesses. And that will mean that when you would write something like array 10, that would turn into a compiler error because it cannot find that reference into the size, into the array, because it won't have generated that function. Of course, for array of for indexing via some variable, you will still need to check if you're within bounds. Some things cannot be solved in this smart way, but it's an example of an idea where it's quite simple, but then you are sort of augmenting the information that you give the compiler to allow it to do things in a much smarter way, which is more or less the theme that Rust does. Buffers for which the size is not known at compile time, Rust only allows those to be put in resizable vectors. Then this is stack. Stack is somewhat easy because it starts somewhere and then you can just do it by the stack pointer. The heap is trickier. Rust is designed, like C, to be compiled to machine code. That means that unlike in Java, there's no runtime environment, no garbage collector, so you need to manage the heap in some other way. You want to be able to not only allocate things, but they need to be freed at some point, because otherwise you get all of these memory leak issues that we saw. And yet you do not want to burden the programmer with calling free, also because they will just mess it up. So you need to be doing something that is a little bit smarter. And what Rust uses is the concept of ownership. It's one of those newer ideas in compiler design, and they use that also to establish how long a variable lives. And how this works is that each variable has exactly one owner. You can declare a variable much like in any other programming language, but then it is owned by that function, and once that function ends, it will be removed. automatically. There's no way around that except by passing it on through another function. So you can pass on ownership, and then when it's transferred to another object, it's moved. And that has the consequence that the original function can no longer access it. So this sort of means that there's always exactly one owner. So it's an example of this in code. We create some value, and then we move it into function, and then you can no longer access it. And this idea allows you to always have at most one owner. And because you then also always know at what point something is owned by whom, you know exactly how long you need that variable to stay around and when you can free it. Because if it goes out of scope somewhere, then you can be safe to remove it. But that also means that you need to be very careful with your references, with your pointers. And if you want to give your value, your variable to some other function, but keep your ownership, you need to pass on a reference. And that other function will be set to borrow the variable. And in Rust, you can have one or more read-only references, or exactly one mutable reference. And what this does is that it makes sure that there are no data erasers. There's only going to be at most one person writing to something and no one reading it, no one else. Or there can be more people reading something, but then no one will be writing for it to it. And that means that if you share some variable between different threads, then it will automatically mean that that thing is read-only, which means that all of these threads can access that thing all the time without having to synchronize. There's of course ways to then make it mutable again through locks and things, but this basic idea already makes it a lot easier also to add multi-threading to programs. And all of this is checked by the compiler at compile time. And that's a very nice feature. You know, either your program compiles and it has this safety, or it will not compile and it was not safe, but it won't exist in that in-between space in principle, where it might work, as in the compiler did its thing and it didn't complain, but So that feeling and not having that is already pretty great. So there are some more tricks though that you need, namely that if you've borrowed something, how do you make sure that it's not being deleted by its owner? Well, the solution there is that the type system is even made more advanced, and that what Rust does there is it attaches a lifetime to the type of a borrowed variable. And the idea of this is if you have a reference, and that reference will live longer than the variable that is owned, the compiler will not allow it to be borrowed. And this is the sort of construction that sort of recalls the thing where you had a function and that function would return a pointer to a local stack variable. This is also such a lifetime problem. The stack variable will go out of scope of the function, which means that the local variable will be gone, the stack will be popped, the local variable will stop existing, but this pointer to it was returned, so that still exists. So then you have a pointer into memory that is invalid. That's the type of problem that we're trying to solve here. And then there's this example that we have here, where we have some variable r and x equals 5. So this is the owner, is within these curly brackets, this variable x will exist. But once we reach the end of it, x will stop existing. And then we assign r the address of x. R will borrow x. And then you will see that the compiler will simply complain you're borrowing X here, but it does not live long enough because X will be dropped at the end of these curly brackets. So sort of what Rust learned is that instead of the standard specifying undefined behavior and then forcing a programmer to avoid it, it will sort of do that work for you. It will just prevent undefined behavior from existing by not allowing all sorts of patterns where that might occur. Admittedly, it's much simpler to write a C compiler because of all of this undefined behavior, because it simply doesn't have to check all of these things. It doesn't have to check if lifetimes of ref pointers or who exactly is the owner of a variable. And that makes it a lot easier to write a C compiler, which is also why they are so ubiquitous on all sorts of platforms. But the much more advanced type system that you get with Rust, by not allowing such behavior and all of that being at compile time, sure, you can have a lot more confidence in the programs that you're writing. And another nice thing that Rust demonstrates is that you don't need a runtime environment. You don't need a sort of overhead from Java or Python that sort of runs your code in a special environment that manages all sorts of things to generate fast code. This was a brief example about Rust because that's the language I know best, and it has a lot of these very advanced features. More of the latest advances in language and compiler design, but it's probably not limited to Rust, and other languages might have parts or all of these features as well. But if you want to learn more about Rust, then there's the website, and there's also the Rust book, which is great and free. But if you want to learn more about all of this in general, type systems, compiler design, I would recommend the compiler construction course, which goes into all of these types of details in a lot more depth, because it's a master's course. So that might be something to keep in mind for in 3 years. You need to start picking courses in your master's, and if that course is still around, I would recommend it because it really gives you a lot of insight into what exactly is happening when your program gets first parsed and then tokenized. Yeah, all the steps that go between having some source code that's at very high abstraction level onto the low levels that end up running on your CPU. That was the side step into memory safety and my Rust advertising. That brings us to the announcements that will wrap up this lecture. So we'll be ending nice on time. So starting with the past, a write-up for exercise 4 is available currently on my website. So if you want to look at an example solution of what the hell you needed to do with the GDB assignment, what exactly was going on with those addresses that you needed to overflow, that's a good place to start. Denisa did a great job on the assembly code in particular that she annotated, and that can be quite helpful if you had no idea what was going on there, or some idea and want just someone to check how your understanding mirrors what was actually going on in that exercise. The solutions to exercise 5, the online thing, will be presented tomorrow by me in the tutorial session at 10:30. I will probably also send that out again as a Blackboard Brightspace announcement. They will be presented tomorrow. I will present breaking the assignment, and we will talk about what exactly was going on there. After the presentation of the solutions, I will have time to answer questions. So that means that I will be looking at the chat window again, and I will answer any questions that you have. Although if you have a lot of questions already, you might want to send me an email so I have some time to prepare if necessary. And after that, I will talk about the exam. The exam will be posted tomorrow. It will be 4 exercises like what you've been doing for the Hackney thing so far. They will be at different difficulty levels, and the last one will again be a full-blown exploit where you need to launch a shell. The deadline is on the last day of the exam period, so the 3rd of July at 6. You don't need to complete them in one sitting. You can just do them at your own pace. You need to break them, of course, but you will be graded mainly on the write-up that you produce. Much less so on if you manage to fully complete all of them and get all of the flags. We will be looking at you demonstrating a systematic approach, your analysis of what you see happening. So can you map what you see onto the concepts of what's going on, which then would demonstrate more or less your understanding of the course material. Do you correctly attribute something to be a return address, for example? Do you see what's going on in the stack frame in that function? And we will be grading those write-ups, and the check mark for I've got the flag is only a very small part of your grade. So if you will only submit flags and no write-ups, expect to fail, just to be clear. The lecture tomorrow will also be recorded, I think. No, it's not really see a good reason why not to. The exam assignments are individual. So that means that you can use any resource. No, you need to do them by yourself. And although you can use any normal resource like books, the internet, you are supposed to solve them by yourself. So don't go around pasting the exercise into Stack Overflow. Don't ask your friends. Don't ask a master student to do anything for you, because please just be a decent human being. Try to include the resources that you used in your write-up, because it's fine to use anything, but if you use something, it's probably also a good idea that you say, okay, I found this, it applies because of that, and I've learned from this. Because that demonstrates the things that I talked about before, the systematic working, the understanding of the course material, etc. You're not supposed to work with other people again. The assignments will not be protected by write or execute or ASLR, and you can expect them to be hideously vulnerable. I think that is enough to say on that. The more advanced protections are very nice to know about, and admittedly you could forget about them immediately for the purposes of the exam, but they are still part of the course in the sense that it's good to know that these things exist and they are part of the learning goals, but it's unfortunately a little bit hard to test for those things currently, because it's a bit stupid to do an open book exam that asks the question, does ASLR prevent ROP? Because yes, and slide 13, right? The parts on memory safety were mainly advertising. So yeah, exam by yourself. I will repeat that tomorrow, and I've today merged some things into the website that allow me to set deadlines, etc. So you can expect the assignments to be available from tomorrow morning until the 3rd of July. Something for those people who have not submitted all of the homework assignments. Again, like I sent in the email through Brightspace this morning, you still need to send me an email and then we can set up a remedial assignment because you do need to have completed the homework assignments to finish this course, to get a grade. That said, if you haven't, we can fix that. So make sure to join tomorrow and make sure to participate in the exam. But send me an email on the assignment situation and then we can talk about fixing that. With that, I think we're done for today. Half an hour, 15 minutes ahead of schedule, but that's fine. So again, tomorrow, assignment 5, the exam and Q&A, and the recording of that will also be made available. Although you might find that it looks a lot like the demonstration that I did in the lecture. Think about what questions you want to ask. I will probably not spoil a lot on the assignments, but yeah, any part of the course is in scope for questions, of course. So if you want me to go over something again, feel free to ask those questions, and I will try to figure out how to get my tablet hooked up so I can draw pictures if necessary. But I've slightly been dreading that, and the solution I used last time was not all that great in the sense that drawing was, even with my nice, very expensive Apple Pencil, was still a bit shitty with that online drawing website. Plus, all of you started to join in. So we need to do, I need to see if I can use something different for that. So hopefully I can draw pictures of stacks tomorrow. With that, I think that we're done today. You can expect to see me again tomorrow, and yeah, I would like to thank everyone for watching these last few weeks, and already wish you a lot of luck with the exam, I guess.